Okay, now it's 9 a.m., so we officially got to start class. So the results of the poll were for both classes, although we only had like 8 people vote in total, but it was
I didn't know how to do it. If I'd known how to do it, I would have done it. I just
okay.
figured it out after the fact.
It was 6 for the exams where I provide everything, and 2 were for crib sheets, and no one voted for open book. So it's going to be tests with closed notes and books, but I provide the information. You're also allowed to ask questions. I will answer definition questions, clarification questions, conversion questions. I won't answer strategy questions. So a strategy question would be like, do I need to convert this to moles? So that's a strategy question. A definition question is, do you calculate molecular weight by summing up the masses times the elements? And I could say, yes, that is how you calculate molecular weight, or something like that. So, or how do you or what is the equation for calculating molecular weight? I can also give you that. That makes sense. But not, hey, how do I do number 2? Right? Okay. So 20 questions, multiple choice, as much time as you want. I found out that the Astro Lab is open after this class, so we also have Sally's class, Professor Irwin's, I should say. Professor Irwin's class is after this one, but if you want to go over, we can go in the Astro Lab. Did you want me to come in early too? Because I know some of you have Professor Irwin right after. Is 8:30 enough time? I mean, is a half an hour going to be enough, or?
What are you looking at me for?
I don't know. Is any? All right. Shoot, I don't have another poll. I'll come at 8. I'll come at 8:30. So you don't have to start at 8:30 if you don't want to. It's going to be a long day for me. Well, a long day for you guys too. But anybody have any questions about the nature of the test? So this is what it's going to look like. You can show your work for partial credit. But there's going to be a lot more space. Like this one here, it's an older test I use, but there's going to be a lot more space in it. So typically what I do in these, I just go through how to set up the problem. And then, because that's what students care about more. I have a video, I'll put it on Lima as well, on how to solve this. So you can watch this video in the lecture archive, you can watch the other one. That's about 20 minutes long over and over again. Some students like to watch it over and over again. But, okay. Let me do this, and I'm going to color code the answers, so I apologize. I'll try, and if anyone is colorblind, I will try to explain it. So, how many of the following compounds are soluble in water? So I'm doing this one blue. So you, of course, the student, will be given a chart. It'll be the solubility chart. And so you don't have to memorize it. And when you use the solubility charts, you will find that the hydroxide, this tends to be insoluble. All alkali salts are soluble. Ammonium salts are soluble, and it's an alkali salts. Those are soluble, so 3 of these are soluble. Soluble means dissolves, so that way. Anybody have any questions with this one? How to do it? So fictional elements, okay, we're changing to pink. Fictional elements is found to have 3 naturally occurring isotopes. The natural abundances are shown here. What is the atomic? What is the atomic mass? So the way that you find the abundance, it's the sum of the mass times the abundance. So this equals 22.176 times 0.45 plus 23.1847 times 0.45, for 45%, plus 24.1934 times 0.1, of course, to 4 sig figs. So, questions on how to do this one? So what precipitate is likely to be formed from a solution containing barium plus 2, sodium plus 1, hydroxide, and carbonate? So again, you have to look to the charts. I'll do red for this one. So you have to, so from these, your options are you can have barium carbonate, you can have barium hydroxide, that's a 2. You can have sodium carbonate, and you can have sodium hydroxide. So those are the combinations of the cations and anions, and you have to look to see which ones are soluble. The chart, so all sodium salts, these are soluble. This one is slightly soluble, and this one, carbonates are insoluble except for alkalis and ammoniums, so this is insoluble. From that, the best answer for this one would be barium carbonate. So, questions with that one? And of course, you'll get the chart, and I'm just getting these together because you combine the positives with the negatives, and I balance them out too. I'm getting some confused looks. Questions with this one? If you don't ask questions, I keep on moving on. Okay.
What was the answer to number 2?
You want me to calculate it out?
No, I just thought you had an answer key. Don't worry.
It's going to be A or C. Probably, I don't know. It's either A or C. So half of that, half of that. Yeah, I don't know. It's going to be.
I can figure it out.
Yeah.
No worries.
Other questions? So we'll go with forest green. What volume in milliliters of 0.0887 molar magnesium fluoride is needed to make 275 milliliters of 0.0224 molar magnesium fluoride? This is where you can use the equation, the M1V1 equals M2V2. So you're looking for the solve for volume. So the V1 is equal to M2V2 over M1. So this is going to be 0.0224 275 all over the concentration in the first, 0.0887. So you're going to need about a quarter, or you're going to need about a quarter of it, so 275 divided by 4, 70 something. So it's either A or B. So whichever one that is. I don't know. I mean, I can't do it in my head closer than 70-ish. So questions on how to do this one? Ooh, empirical formula. All right. So what color? I'll do black. Black like my soul. Okay. What is the empirical formula of a substance that contains 2.64 grams of carbon, 0.444 grams of hydrogen, or 3.52 grams of oxygen? So you do these, you convert first to moles. Mole carbon to 12 grams carbon, mole hydrogen to 1 gram hydrogen. mole oxygen, this 16 grams oxygen. I'm using that from the periodic table. I know it's 12.01, it's 1.008, but it's, oh, sure, I'll make you feel better. I'll do the bigger digits. Guess I shouldn't be sloppy. Okay, and you do need your calculator. I can't do this all in my head. 2.64 divided by 12. Oops, I should do 12.01. Oh, jeez, come on. Oh. 2.64 divided by 12.01. 0.2198 moles carbon. 0.44 divided by 0.8. 445 moles hydrogen. 3.52 divided by 16 is equal to 0.22 moles oxygen. So you divide all of them by 0.22 and you get 1 to 2 to 1. So it's going to be carbon H2O. So how to do this one? You want the empirical formula. So you take the mass of each. Here's carbon, here's hydrogen, here's oxygen. You divide by the molar mass, and you get 0.022 moles carbon, 0.44 moles hydrogen, 0.22 moles oxygen. You divide by the lowest number, which is 0.22, so you get a 1 to 2 to 1 ratio. So carbon, hydrogen to oxygen, and nothing there indicates a 1. So questions with this one? Okay, ooh, another long one, shoot. Determine the percent yield of reaction when 28.65 grams of carbon that produces 20.65 grams of carbon when 50 grams of iron oxide react with excess aluminum from the following reaction. Okay, so we gotta get the theoretical yield. So the theoretical yield, and this is a new color, blue, and I'm writing it was for number 6. Theoretical yield, this is going to be equal to, we're already given eliminating reagents. It's 50 grams of iron oxide, excess aluminum. So 50 grams Fe2O3, and then mole Fe2O3. Gotta get the molecular weight. So Fe2O3, this is going to be 55.85 plus 3 times 16. I think it's 55.85 for iron, isn't it? Yep. 55.85. You don't have to memorize the periodic table. All this times 2. It's 2 irons. 2 times 55.85. 2 times 55.85 plus 3 times, jeez. I keep on hitting all clear. 2 times 55.85 plus 3 times 16. 159.7. So that is 159.7 grams Fe2O3. And what are we looking for? Iron. 2 moles iron, 2 mole Fe2O3, and 55.85 grams iron per mole iron. So where am I getting the the 2 mole per 2 mole iron to 1 mole Fe2O3. I'm getting it from the balance of the chemical equation. Here's 2 here, here's 1 there. And then calculate out the theoretical yield. It is 50 divided by 159.7 times 2 times 55.85, and we get 34.97. And now the percent yield is the actual over the theoretical, well, times 100. So this is going to be 28.65 divided by 34.97. Okay. 28.65 divided by 34.97. Oh, wait. Did the number incorrectly. 28.65. That's why I do the numbers at the end of the calculator, because this is sometimes the hardest part, is putting the numbers in your calculator correctly. That's 81.93%, which is that one. So questions with this one, it's a limiting reagent problem. Well, you want the percent yield. You're given the limiting reagent because of the words excess aluminum, so the limiting reagent is iron oxide. So you calculate out the theoretical yield by assuming all the iron oxide reacts. So you have so start off with the iron oxide, divide by the molecular weight to get the moles, convert to moles iron using the balanced chemical equation, then back to grams using the atomic mass of iron to get about 35 grams of iron being formed. And then you take the actual yield divided by theoretical yield times 100%, so 28.65 divided by 35, and you get 82% as the theoretical yield. And that is, of course, one of the answers. So, questions with how to do this one? Okay, so which species is represented by the following information? So you have to look to the periodic table. And so the number of protons, so let me change. I do lime green. You can see, it's a little light for you. How about brown? Can you see brown? Yes, you can. Okay. What looks on the iPad is different than what looks like on the screen. So what species is represented by the following information? So you have to look for something that has 12 protons, and it's magnesium. So you know that the element is magnesium, and you look to the periodic table. So something that has 12 protons is magnesium, and you'll have a periodic table in front of you. But if you can see, there's a 12 on top of magnesium. That means that there's 12 protons. So you know that the element identification is magnesium, and then neutrons, that just is a different isotope. But electrons 10. So if you're missing 2 electrons, that means there's a +2 charge on it. And also, if you want to go further, if for a specific nucleotide, this would be 12, and then 12 plus 14 would be 26. So it would be magnesium 26. That's just the top number is the protons plus the neutrons. The bottom number is the protons. But it's not asking for that. So you just have to indicate the +2 charge. And the +2 charge is the fact that there's 2 fewer electrons than there are protons. And remember, the number of protons defines the element. So, questions with this one? Okay. How many moles of copper oxide can be produced in 0.9 moles of copper 1 oxide in the following reaction? So 2 copper 1 oxide plus oxygen makes 4 copper 2 oxides. All right, so this is another, I'll do it in red. So how many moles of copper oxide? So I mean, you can do dimensional analysis. That's easy, but you can also do the ratios. You know that there's a 2-to-1. There's twice as much copper 2 oxide, so it's going to be 0.9 times 2. So you can jump to A right away if you want. But if you want to do dimensional analysis, you can go 0.9 moles copper 2 oxide times 2 moles. Well, I guess I'll use the numbers in the balance equation. 4 moles copper oxide to 2 moles Cu2O. And I'm just getting that from those numbers there that I've highlighted. So there's a 2-to-4, 1-to-2 ratio. And then, so if you carry out the math, 0.9 times 4, that's 3.6 divided by 2 is 1.8. So the answer is A. Questions on this one? Okay, changing to blue. How many grams of oxygen are formed when 6.21 moles of potassium hydroxide are formed? So you have the KOH here, and so let's see here. So you start off with 6.21 moles KOH times mole O2 to 4 mole KOH, and then 32 grams O2 per mole KOH. So that's, I'm sorry, not mole KOH, mole oxygen, sorry, mole O2. So looking at the ratio here to here is where you get this step. And then 32 is just 16 times 2 for oxygen. So what would that be? That would be 6 times 8. That'd be 48. That'd be 49.68. Okay. So that's A. So 49.68 or 3 sig figs. There. Okay.
Can you say that? Thank you.
Can I what?
The screen was just on.
Is that better?
Yeah, that's great. Thank you.
So once the mass of oxygen for given the moles of KOH, so dimensional analysis, convert to moles oxygen, then the molecular weight of oxygen, and then get that and then do the calculation. Questions with this one? Determine the number of protons, neutrons, electrons the following. 40 or element X that has 18, the bottom number 18, the top number 40. 18 is the protons. So I guess, so in pink here, the bottom number is the number of protons. This is the number of neutrons plus the number of protons. So protons is 18. Neutrons is 40 minus 18, which is 22. And the electrons, so there is no charge, therefore it is 18 electrons. So we have 18 protons, 22 neutrons, and 18 electrons, which is choice D. So if there would be a charge, like if there was, if it was 40, 18x plus 2, this would be 18 protons, 22 neutrons, 16 electrons. And if it was x minus 2, this would then be 20 electrons. So negative means extra electrons, positive means fewer electrons. Questions with this? Balance the chemical equation to go below and determine the number of moles of iodine. I'll give an indigo color because that's kind of what iodine looks like. Or purple. It's either, I'll do purple. I'm already on indigo, what the heck. Okay, balanced chemical equation. So start with aluminums. There's 2 on the right, so we can put 2 on the left. And on the right, there are 6 iodines, so you need to have 6 iodines on the left. So on each side of the equation, we have 2 aluminums, and we have 6 iodines. So that's balanced. And determine the number of moles of iodine that reacts with 30 grams of aluminum. So that would be 30 grams. Okay. So we know on the left, 30 grams aluminum. Then there's mole aluminum to 27 grams aluminum. Again, you do not have to memorize the periodic table. And then moles of iodine. And then there are 3 moles iodine to 2 moles aluminum. So that's going to be 1.5-ish moles. So it's going to be B. So the answer is B. So, make it smaller. So this one here, same idea, dimensional analysis. We're starting off with 30 grams aluminum, and assuming you balance the chemical equation properly, but then use the periodic table, get the moles of aluminum, and then just from the balance equation, transfer the molar ratio between iodine and aluminum. There, it's Al, I should say. Moles Al. Questions with this one? All right, if the density of ethanol is 0.789 grams per milliliter, how many milliliters of ethanol are needed to produce 15 grams of carbon dioxide by the following chemical equation? So I'll do red. So we need 15, so we need to produce 15 grams of carbon dioxide, and we need milliliters of ethanol. So dimensional analysis, start with what we know, 15 grams carbon dioxide, and we're going to work our way towards milliliters. So we're going to convert to moles CO2, then convert to moles ethanol, and then convert to mass, and then use the density to get the volume. So 15 grams CO2. Mole CO2, it's 44 grams per mole, and that's for 12 for carbon plus 2 times 16 for oxygen is 44. It's 44.01, but meh. Then, so then what do we do after that? So then we gotta get to moles. Moles ethanol, mole C2H5OH. To 2 moles CO2. Molecular weight of ethanol, let's see here, it's going to be 2 times carbon, so 24 plus 6 plus 18, or 16, so that's going to be 48 grams. 48 grams C2H5OH all over mole C2H5OH. Is that right? 2 times 4 is 24 plus 6 is 30 plus 16. Shoot, it's 46. 46 grams. Sorry. It is 46. Is that right now? I'm doubting myself. 30 plus 16, yeah, that's 40. 46, and then we need the milliliters. So then that's milliliter per 0.789 grams. C2H5OH. C2H5OH. And this, usually the dividing of the density is what gets the students. So if you look at the units, it's 0.789 grams. So make sure that that's on the bottom. And why do you put it on the bottom? So that way the units, grams ethanol will cancel, and you get the milliliter as ethanol on the top. So that's going to be 7.5. It's going to be around 10. So it'll probably, I think the answer is D. So, right, because then that's about the same. So that's 7. Oh, wait a second. No, it's going close to 20. What am I saying? Oh, wait, divided by 2. 7.5. Oh, no, that is 10. And I might as well calculate it out. 15 divided by 44 divided by 2 times 46 divided by 0.789. Yep, it's I'm going to do 9.94, which is D. Okay. So again, the students usually have a hard time understanding this one. The main reason is because it's divided by the density. So start off with 15 grams of CO2. And since we're doing dimensional analysis, start with what you know, work your way towards what's asking. It's asking for milliliters of ethanol. So start off with 15 grams carbon dioxide and convert to moles. And then a mole CO2. Mole CO2, we can get moles of ethanol. And the moles of ethanol are determined by the balanced chemical equation. So mole ethanol to 2 moles CO2. And then convert back to mass ethanol using molecular weight. And then looking at the units, we're at grams ethanol. And the units in density are grams per milliliters. So you have to divide by it. So put the milliliters in the top and put the grams in the bottom. And then get about, put it all through, get about 10 milliliters. Questions with this? All right, so I'll go purple. We haven't done purple yet. Do you see purple? Yes, you can. Anybody see the new Joker movie out of curiosity? Is it good? Yes. Okay. We're seeing. All right, I haven't seen it yet. Does it wear purple? Oh, man. All right.
It's a shade.
It's a shade. Mm-hmm. All right, well, which of the following pairs will form a precipitate? So when you do this, I'll start off with ammonium nitrate. So like for part A, you look for NH4NO3 plus Li2CO3. You look. I'll change colors. The reds are going to mix with the greens. So what I've indicated in red is the NH4 and the CO3, and in green I've indicated the nitrate and the lithium. So those two are going to mix, and you have to ask yourself, is one of these insoluble? And it turns out for this one has no reaction because the all ammonium salts and all alkali salts are soluble. So then you go to number B, and in the chart, it'll say all acetates. Acetate is C2H5O2. Those are all soluble. All nitrates are soluble, so B is a big old no reaction. So D is the sodium and lithium are alkalis. D, both of those are soluble. Then the question is, for C, so you should look to C, and when these mix, I'll choose different colors. I'll pick yellow and purple. Most people can see this. So I've indicated Hg mercury in yellow and iodine in yellow, and then nitrate NO3 and lithium in purple. And you have to look to see, does one of those form a salt that's insoluble, and Hg2 plus 2 mixed with iodine does, the iodine, this is in fact forms a solid. So that is a precipitate. So that's an exception to the rule. So what do I mean? I guess I should just see the chart. That would be it's going to be 5A. So this chart here, which you'll be given, because for iodine, mercury plus 2 is an exception. Iodines tend to be soluble, with the exception of silver, mercury, and lead. Mercury is an exception. Oh wait, I should. Mercury is an exception, therefore it forms a precipitate. So C is the one that would form a precipitate. So, questions with this one? How many molecules of hydrochloric acid are formed when 50 grams of water reacts according to the following balanced equation? Assume excess ICl3, which means limiting reagent, and they told you, I'm going back to blue, I like blue. How many, so it's a limiting reagent problem, and since we've assumed that this is excess, it's the water is limiting reagent. So our water is limiting reagent. So 50 grams of water. So we have to get to molecules HCl. So how do we get to molecules HCl? We convert 50 grams of water to moles of water. Then we convert moles of water to moles hydrochloric acid. And when we get moles hydrochloric acid, we can then use Avogadro's number to get the number of molecules. So mole water to 18 grams water. And then we have 5 moles HCl to 3 moles water by the balanced chemical equation, because there's 3 in front of the water and 5 in front of the HCl. So now we're at moles HCl. Then we have 6.02 times 10 to the 23rd. That's an ugly 2, 3. 10 to the 23rd molecules HCl per mole HCl. So let's see here. I'm going to do this in my head. That's going to be about 2.5 moles times 2.6, about 4. So it's going to be about 25 by 24. I'm guessing it's A. I'm getting about, in my head, guesstimating it's about 2.5 times 10 to the 24. So I think it's A. But I better check it. I have time, what the heck. 50 divided by 18 times 5 divided by 3 times 6.02 E3. Yep. I'm actually getting 2.79, but close enough. So this one is a little different because it's asking for molecules, but a mole is 6.2 times 10 to the 23rd of whatever. It's like a dozen is 12 of whatever, a mole is 6.02 times 10 to the 23rd. Same idea though. Limiting reagent problem, we start with 50 grams of what we know and do dimensional analysis, get the moles of the reactant. Now we convert to moles of product, and in this case, multiply by the number instead of the molecular weight to get, because a lot of times it asks for mass, but this time we're asking for individual molecules. So, questions with this one? So automotive airbags inflate when sodium azide explodes by this equation. 2 sodium azide plus equals or yields 2 moles of sodium and 3 moles of nitrogen gas. How many moles of nitrogen gas are produced by a composition of 2.88 moles of azide? So I'll go to black. So 2.88 moles NaN3, and we just want moles N2. It's just 3 moles N2 to 2 moles NaN3. This is pretty easy. So that's 1.5. So plus 1.44. That's 3, 4.32. Yeah. Like so. So this one is just a one-stepper, which is nice, rather than many steps. Questions on this one? Looks so easy when I do it, right? Ooh, a hard one. Determine the linear reagents and the mass in gram of nitrogen that can be formed from 50 grams N2O4 and 45 grams of N2H4. Some possibly useful molar masses. Oh, we took the fun out of it. N2O4 is 92 grams per mole, and hydrazine is 32 grams per mole. So, okay, so we don't know. I'll do red. Or can you see orange? We haven't done orange yet. You see, yes, you can see orange. Okay, it's October. We're getting to the pumpkin spice everything. So 16 is now pumpkin spiced. So start off 50 grams N2O4 and 45 grams N2H4, and then maybe I'll bring this one down a little bit. So let's see here, N2O4 mole, N2H4, N2H4. Oh wait, there. O4. Jeez. O4. 45 grams. No, wait, that's 90. Ah, got up on the wrong side of the coffin this morning. So convert to moles, and what do we want? We want nitrogen. So 3 moles N2 over mole. Okay. So setup for this one. So 50 grams N2O4, 45 grams N2H4. If I want to use names, this is dinitrogen tetroxide. This is dinitrogen tetrahydride, also known as hydrazine, but doesn't really matter for this problem. Moles, nitrogen oxide over 92, given there. Then convert 3 to 1, and then nitrogen is 14 times 2, periodic table, 28 grams per mole. Hydrazine, so mole to 45, 32. Shoot. $32.05. So mole to 32, and there's 3 moles nitrogen to 2 moles hydrazine, and the same mole, 28 grams per mole. And you just have to do them both. So let's just go ahead and do them both. 50 divided by 92.02 times 3 times 28. This is 45.64. That's grams nitrogen. So 45 divided by 32.05 times 3 divided by 2 times 28. This is 59. That means that N2O4 is our limiting reagent, and we form 45.6, and that's that one there. So questions with this one? So what is the oxidation number in chromium atom and the K2CrO4? It's +6. No. The way you solve this one is you'll be given the rules, and the sum of a neutral compound. I'm using pink for this one. So 0 is 2 times potassium plus chromium plus 4 times oxygen. And if you look in the rules, potassium tends to be +1, 2 times +1, plus chromium plus 4 times -2. And so that means that 0 is 2 plus Cr -8 equals chromium -6 is equal to 0, or chromium equals 6. So that's +6. Questions with this one? Okay. Anybody want to pick a color? Green. How many molecules of sucrose are contained in 14.3 milliliters of 1.4 molar sucrose solution? So dimensional analysis, we have then 0.14 mole sucrose per liter. That's a definition of molar. It's moles per liter. And then we have 14.3 milliliters. So, but then there is a liter to 1,000 milliliters. And then if you look at the units, the milliliter is going to cancel, And then the liters are going to cancel, so we're left with moles of sucrose. And then it's just 6.02 times 10 to the 23rd molecules sucrose to moles sucrose. So the 342.3 grams per mole is just there to throw you off, really. So just calculate that out. So let's see here. So 14 squared. So 20, 14 squared. Oh, I can't do 14 squared in my head. I'm just going to do the calculator. Can anyone do 14 squared in your head? I can't do 15 squared in my head either. 0.14 times 14.3 divided by 1,000 times 6.02 and 1.2 times 7 to the 21. Yeah, 1.2. 1.205 times 10 to the 21. Which is B. So you get this one. So 0.14 molar means 0.14 moles per liter. And we're given the volume, 14.3 milliliters, but then we have to convert to liters. So convert milliliters to liters to get this to liters. So the milliliters cancel, and then we have moles. Now we need to go. That's molecules, SUC, sucrose. That's SUC that's shorthand for sucrose. So if you ever go and study more sugars and people put SUC on the board, that means sucrose. Like GLU is glucose, and something like MAN is mannose. So if you take other sugars, so I'm trying to get you to get some of the jargon in case you take other higher classes. So, but then yeah, it turns out to be 1.21 times 10 to the 21. Questions with this one? And the sneaky part is you're given extra information that you don't need. Okay, back to blue. What is the mass of half a mole of difluoromethane? So half a mole, well, so 0.5 mole CCl2F2. And you gotta look at the periodic table for the molecular weight of this. It's going to be 12 for carbon plus 2 times 35.45 for chlorine plus 2 times 19 for fluorine. So let's see here. That'd be 70.9 plus 38 plus 12. So 70.9 plus 50. That's 120.9, I think. Is that 120.9? It's a lot of numbers to hold in my head. Let me double check that. 12 plus 70.9 plus 38. Yep, that's right. Times 120.9 grams CCl2F2 to mole. CCl2F2, so it's 60.45. 60.45, which is A. Questions with this one? Hopefully this is an easy. That's one thing is sometimes you're so used to doing the hard ones, and you get an easy one that kind of throws you off. And here's another easy one that a lot of students get wrong. So what is the mass of a single fluorine atom? So let's see here. So it's, and the way you do this one, it's 38 grams fluorine to mole fluorine. Fluorine is 18 times 2, just showed. And then mole F2 all over 6.02 times 10 to the 23rd molecules. So it's going to be 38 divided by Avogadro's number. So 38 divided by 6 is going to be about 5. I think it's A. I'm guessing it's. Let me double check though. Come on, calculator, or come on, phone. Don't fail me now. 38 divided by 6.0223. Yep, 6.31. That's grams per molecule. I think what I'm getting 6.3123, and I think it's because I didn't, because Avogadro's number is 6.022. So if I carry out the 4 sig figs, let me do that now. To double check. 38 divided by 6.02223. Yeah, if you carry it out. If you carry it out to 4 sig figs, you do get exactly the right answer. Okay. So this one as well, I can't stress enough, dimensional analysis is the way to go. But the mass of a single fluorine atom, and so fluorine, F2 fluorine is 38 grams per mole, and then divide by mole over number of molecules to get, the moles go away, and you get grams per molecule as your units, like so. So, ta-da! This test has now been done and explained. So, does anybody have any questions? Anything you want me to go over again?
Yeah, could you review sig figs?
Sig figs. Okay. Sig figs. Sig figs themselves or sig figs and calculations? Okay.
Just to know for hall review of how it works.
So significant figures. Rule number 1, all non-zero digits are significant. So interior zeros are significant. Zeros to the left are not significant. Zeros to the right are significant. Well, if after decimal point are significant, before a decimal point are significant, and trailing zeros are implied before, well, trailing zeros before a decimal point. These are implied, but they should, it's better to use scientific notation. It's ambiguous. So sometimes you get a point after it to tell you that they are insignificant. So, okay, so let's talk about examples. All non-zeros are significant, so 28.03. 2, 8, and 3 are significant, but then interior zeros, number 2, the interior zero is significant, so 28.03 has 4 sig figs. So 408, that has 3 sig figs. So 0.0032, the zeros to the left are not significant, So 0.0032 has only 2 significant figures. So zeros after decimal point are significant. So 45.000 has 5 sig figs. So the 4 and the 5, and then the 3 zeros after it. So 140.00, the interior 0 is also significant. So this one, 140.00, also has 5 sig figs. And if there are zeros after the number, it's ambiguous. So, like if I say the age of the universe is 14 billion years old, that's ambiguous. You're like, how many figs is that? Because that's we know to better than it's 13.8 something something, but it's the 14 billion. Does that have, so billion 3, does that have 11 sig figs? No. It has, that's hard to say if it has 1 or even 2 sig figs with a number like that. So that's implied. It's better to use sig figs. So something like, say the universe is 13.8 times 10 to the 9 years old. That would tell you right away that's 3 sig figs. Okay. Questions with that? Then calculations. Basically calculations, when you do multiplication division, you take the number of sig figs down to whatever you have the lowest of, and addition and subtraction, the sig figs stop at the lowest measurement. So for these, for example, this 2.345 and adding 0.07 and 2.9975, you only know the answer to the hundredths place. So the answer has to go down to the hundredths place, and then for like these multiplications, like top one, 4 sig figs times 5 sig figs times 2 sig figs, you get an answer with 2 sig figs. So the multiplication division goes down to the lowest amount of sig figs. Addition and subtraction goes to the lowest of the measurement that you have available. And then the sig figs are determined after that. Questions with this? Okay. Other questions? So in that case, there's no reason to keep you. So you may leave, and I will answer any questions if you want to ask me afterwards. And I'll